All right, this is geometric sequences and series. And so I guess we'll do some definitions. Geometric sequence is a sequence that moves from term to term through multiplication of a common ratio r. All right, geometric series is the sum of a geometric sequence. Nothing more. All right, find the first 5 terms of the sequence, determine if it's arithmetic or geometric. Again, arithmetic being adding or subtract. I know you don't know that. Geometric would be just multiplication or, division. Because division is multiplication. It really is. So you're supposed to find the first 5 terms. So you're going to feed it a 1 and you're going to get an 8 back because 3 times 1 is 3. Add 5 and blah, blah, blah. I bet the next one's 11. If I feed it a 2, well, by gosh, it's 11 because I noticed this 3 here. If I feed it a 3, I bet I get a 14. We'll see. And I do. Plus 3, slope, lines, all that good stuff. Ace of 4, if I feed it a 4, I guess I'm going to get a 17. And ace of 5, if I feed it a 5, I reckon I'm going to get a 20. This is arithmetic. It has a common difference of 3. All right, next one. You got to feed it an exponent. Probably geometric. Ace of 1 would happen when you plug in 1. And 3 to the first is 3. You add 5, you get 8. Ace of 2 would happen when you feed it a 2. And 3 squared is 9. Add 5, you're at 14. And ace of 3 happens when you plug in a 3. Well, 3 cubed is 27. 27 and 5 is 32. And ace of 4 is going to be a 3 to the 4th. Add 5. And 3 to the 4th, I feel like that's 81. Add 5, you get 86. And then ace of 5 is 3 to the 5th. Add 5. And 3 to the 5th has been 243 since I was a little kid. I don't think it's changed. 248. There you go. It's obviously geometric. I'm just pausing. I'm thinking about something right now. I want to see if it's worth teaching or not. I was trying to decide if I was going to teach like an old pattern here or not, but I don't think I'm going to. I mentioned that we used to teach a lot of things back in the day that we don't anymore. Now, is this geometric? Well, geometric has a common ratio. So I'm going to take 14 and divide it by 8. And if you like decimals, that's 1.75. So what I'm doing is I'm comparing terms here. I'm going to take 32 and divide it by 14. And it's not the same. It's it's a fraction, but it's not the same. It's about 2.29. So there is no common ratio. So this is definitely not geometric. It's an exponential function is what it is. And I was trying to decide if I should teach you how to find the pattern to these or not, but I decided not to. All right. Moving on to number 3. The nth term is 4 times 4 to the n minus 1, so we're just going to plug in a 1. And if we plug in a 1, the exponent becomes 0, and you get a 4 back. If we plug in a 2, the exponent becomes a 1. 4 times 4 is 16. If you plug in a 3, the exponent becomes a 2. That's going to be 4 times 16, which is 64. You plug in a 4, the exponent becomes a 3. 4 cubed is 64. 4 times 64 is 256. And if you plug in a 5, the exponent becomes a 4. 4 to the 4th is 256 times 4 again is 1,024. And, you should be smart enough to tell that right here, we're multiplying by 4. So yes, this is geometric. It has a common ratio of 4. And then we got number 4. And it's just simply 4 to the n. It's really simple. Plug in a 1, you get a 4. Plug in a 2, you get a 16. Plug in a 3, you get a 64. You plug in a 4, you get a 256, and dot, dot, dot. It's the same one. It's the same one. It's just written differently. These two are actually the same exact sequence. Kind of interesting, huh? Why? 4 is 4 to the first. And this is 4 to the n minus 1, which is actually 4 to the n over 4 to the first. You'd know that if you learned your properties about exponents. Remember, x to the a over x to the b is x to the a minus b. And what happens there is they cancel. They're the same exact thing. That's why it's in the notes. Just kind of interesting. Explicit and recursive rules for geometric sequence. The explicit rule, which is the straight and to the point, is a sub n is the first term times r raised to the n minus 1. Give me, I'm tired. And the recursive rule starts off a lot like the geometric one. It's a piecewise function. Your a sub 1 if n is 1, and your a sub n minus 1 times r if n is bigger than 1, because this is about multiplication. So it looks just basically the same as the arithmetic, but it's about multiplication. All right, write the recursive and the explicit rule for the following sequence and try to write the explicit rule 2 different ways, because you can. So here what I notice here is we're multiplying by 3 as we move on. So my ratio is 3, and my first term is 4. And the explicit rule is going to be a sub 1 times r to the n minus 1. So it's going to be 4 times 3 to the n minus 1. Now, can this be written 2 different ways? This one might be a little bit different. You can. I can think of this 3 to the n minus 1 as 3 to the n over 3 to the first. I can put these together. That'd be 4/3 times 3 to the n. And they both are the same rule. Kind of interesting. Moving on to number 2, this is going to be one of these where we multiply by 4, I think, by 2. Now, obviously, when I see this thing, I see powers of 2. I actually see 2 to the first, 2 to the second, 2 cubed, and so forth. Oh, I forgot to write the recursive rule, didn't I? My bad. First term is 4 if n is 1, and then the previous term times 3 if n is bigger than 1. I'm going to pause. I've got a tired headache. Just give me a minute. All right, the struggle continues. Anyways, we're multiplying by 2. So let's start with our explicit rules. Remember, we're the first term, which is a 2, times the ratio, which is also a 2. And the exponent is n minus 1. Or, again, think about, I don't know why I put the fraction there, but think about this 2 to the n minus 1 is 2 to the n over 2 to the first. And the 2's cancel. They both work, okay? Your recursive rule, again, the recursive rules are like ridiculously easy. You just plug stuff in. Your 2 if n is 1, and you're the previous term times 2 if n is bigger than 1. Words. Bob, the incredible shrinking man, loses half his height every 10 years. Bob's height peaked when he was 16 at 6'4". He is about to turn 26. write out the first 5 terms of Bob's declining height. Okay. So let's convert 6'4" into straight inches because we don't want to do 3'2" and then something else. Like it's going to get harder. Okay. Because the next thing would be like 1.51. So make the thing in inches. All right. So there's 12 inches in a foot. 6/12 is 72. Add 4. This is 76 pure inches. So the first term is 76. We don't actually have to write a rule, at least yet. The second term is going to be half of that, which is 38 inches. The third term is going to be half of that, which is 19 inches. The fourth term is half of 19, which I'm pretty sure is 9.5 inches. And then the fifth term is half of that, which should be 4.75 inches. All we had to do was cut it in half. Now, is this a geometric rule? It sure is, because we just figured out, by reading here that the ratio is a half. So my explicit rule is that I'm Bob's first height, which is 76 inches, times a half to the n minus 1. Easy peasy, lemon squeezy. And this would be, how long will that take? 11 minutes? I think we need to introduce the summation formula. That way I can really spend some more time on it tomorrow. So the sum of a geometric series is going to be a little bit different than the sum of an arithmetic series, obviously. But it is the first term times 1 minus r to the n over 1 minus r. Once upon a time, I had a class prove that to me, but that was a long time ago. But anywho, that's the formula. All right? It's not too bad. It's really not. You just feed it the ratio in the first term. And of course, you know how many things you have. And let's do one of these. Find the sum of the first 10 terms of the geometric sequence 1, 2, 4. So the ratio here would be 2, wouldn't it? Multiply by 2. The first 10 terms would tell me that n is 10. And the first term is right there, base 1. So we're going to find the sum of, then let's go ahead and write the formula down too. It's not going to kill us to write it down. So the sum of 10 things here, because n is 10, is the first term, which is 1, times 1 minus, and you should probably always put that r in a set of parentheses. That matters when it's a negative, and that does occasionally happen. Sometimes the ratio is negative. We'll do some sequences like that. Anywho, 1 minus 2 to the 10th power. That's sitting pretty over 1 minus 2. This one, I wouldn't expect you to do it in your head. I don't think there's a teacher in this country. Well, I take that back. Like, if I had a pure group of honors kids, like nothing but a class of honors, and it wasn't a self-selected honor system like we have now, I'd probably make kids do that by hand. Because they can. There's a 1 out front. We have 1 minus, and again, it's good safe practice there to put that in a set of parentheses. And that's all sitting over 1 minus 2. And if you don't know what 1 minus 2 is, the TI-84 is not going to judge you. Although I'm not going to lie, I feel kind of stupid pushing 1 minus 2 in a calculator like that. But I did. 1,023. And that is a good stopping point for day 1 of geometric sequences. Because we introduced a summation form, we did several. It's a good stopping point.